Hello students, welcome to next class. Okay, 7. In the previous video we have learned regarding the AgCl conduction. Okay, so two types we have seen: interstitial movement of Ag plus and interstitial C. Okay, that is knock on. So this is the real conduction paths which takes place, okay, which was got from the equation, okay, from the diffusion as well as conductivity, that is D is equal to KT divided by F of mz d square. So this we learnt in the previous video, and I said both NaCl and AgCl, okay, so they have rock salt structure. Yeah, but the distance, the small difference is here. The vacancy mechanism is prevalent, dominant in the Na plus ion, which moves from one corner of the cube to another corner via interstitial site. Okay, and we have learned this much in the previous video, while as in interstitial C was found in AgCl. Now going to next, the effect of impurities. Okay, divalent effect of divalent cation impurity on extrinsic conduction, okay, region of AgCl. So if you see here now in this extrinsic region in NaCl also we have learned, but if you see in AgCl it is somewhat different in AgCl. So we will have some two graph here to understand this concept, okay, of AgCl, like this. So this is inverse of temperature per Kelvin and versus log of sigma, that is your conduction. So I can do something like that, some like this. Okay, so we can extrapolate here this way, like this. Okay, so we'll see that what is this. So one more diagram we will have it here, same diagram like this. Okay, and you can start like that. Here also something like T1 T2. Okay, so this is what you can extrapolate like this. Here also extrapolate. Okay, so this is your intrinsic region. Okay, this is your extrinsic region 1, and this is extrinsic region 2, extrinsic region 2. Okay, and this is your temperature T1 T2, where T2 temperature is greater than T1. Okay, so same thing here. So this is your log of sigma, and this is the temperature. Okay, or you can see the cadmium plus 2 concentration. Okay, because impurity concentration, and this is what the temperature. So both we can having here the graph, it is inverse of temperature's log. So we are having this one. So this is also of AgCl with respect to Cd plus 2. Okay, cadmium concentration, and this is also the cadmium concentration dip is there, then increases there. So here this thing you have to keep in the mind here, and according to this graph we are going to now explain the effect of cationic in extrinsic conduction region of AgCl, which is quite different from NaCl. So NaCl we have learned, but that is different from this AgCl. Okay, now here you can see the presence of Cd plus 2 increases the number of, what happens, the presence of Cd plus 2, if you put this Cd plus 2 impurities, what will happen, the presence of this increases the number of cation, definitely number of cations. Okay, vacancy is improved. Okay, cation vacancy, obviously this is plus 2 cations, so if we put this, the number of cation vacancy will be increased. Okay, so number of cation vacancies, but because of the product of concentration of cation vacancy as per the equation, so cation vacancy and if you see, and Ag plus interstitial is equal to constant. Okay, so in previous video we have seen that the Na plus and that of Cl minus will equal to constant. Okay, vacancies V of Na plus. Similarly here also, so V of Ag plus interstitial plus V of cation vacancy is equal to constant. Okay, so this is what equation we have to keep in the mind. So what happens here, now if the interstitial Ag plus concentration, if we increase this, okay, if we increase this, that is your cation vacancies, cation vacancy, if it increases, the interstitial Ag plus concentration will decrease, because it has to maintain constant here. Okay, if the cation vacancy by addition of CD plus 2 is increased, okay, by adding this one. So what will happen, which is the main mobile here, Ag plus interstitial, that will decrease, okay. So that as per the equation, so this will decrease, okay. So concentration of cation vacancy and Ag plus interstitials, as it is constant, the interstitial Ag plus has to decrease now, should decrease here with increasing in CD plus 2 concentration. So the addition of CD plus 2, therefore what happens, this reduces the mobility of the Ag plus ion. So this reduces the mobility of the Ag plus ion, and an extrinsic region at low temperature is observed at lower sigma. That's why you can see here lower sigma is observed here. See, okay, that is why, because this is decreased. Okay, the mobile Ag plus interstitial concentration is decreased. So we can find here the depth here. Okay, so sigma value also low value is obtained here. Okay, and the degree of this decrease displacement increases with increase in the CD plus 2. As you increase the CD plus 2, this decrease, there will be decrease in this sigma value. Okay, due to more you can say numerous mobile cation than the more numerous cation than the mobile cation, that is Ag plus interstitial. Okay, so here the degree of you can say displacement, okay, increases with increase in the CD plus 2 concentration. So this displacement is there, so it will increase with increase in the concentration of CD plus 2, causes a minimum conductivity, okay, there is a minimal, until there is a minimum conductivity reduced, until a minimum conductivity reduced. So this happens until a minimal minimal conductivity reduced, this will cause the effect here. Okay, so once you can see the conductivity due to more numerous, okay, more numerous you can say mobile cation will be equal to the that of less numerous but more mobile interstitial Ag plus ion. Okay, so when this becomes the criteria here, so what happens here, a high defect concentration of cation vacancy is dominant. High cation vacancy will be dominant. Okay, so defect of due to cation vacancy will be more here. Okay, and again what you are going to see, so that because of this cation vacancy migration predominates, again there is increase in the sigma value here, like this. Okay, so again when there is a cation vacancy dominance will be there here. Okay, more number of mobile interstitial Ag plus ion. Okay, so that time what will happen, the cation vacancies migration is predominant here, high defect will be formed here. And what will happen when the equilibrium is installed between the more cation vacancy, okay, and but less mobile ions will be equal to less Ag plus minimum but more mobile ions. So this equilibrium when it is observed, what will happen because of this, what will happen, the numerous what will this one the cation vacancy migration predominates. Okay, the cation vacancy migration predominates. Okay, and because of this, the further we can see there is a large increase in the conductivity here. This is what shown in here in this diagram here. Okay, so initially what will happen, there is constant here, but suddenly there is dip here. Why? Because here what happens, as you increase the cation here impurity, what will happen, this will decrease. Okay, so early this will decrease. Okay, what is that, Ag plus ion interstitial will decrease. So there will be sudden decrease up to how much, up to a minimum value, minimal value, till there is a equilibrium between whom, between this. Okay, so between less mobile but numerous cation vacancy will be equal to more mobile but less Ag plus ion interstitial. So when this equilibrium is maintained here at this much, it will go down, and afterwards what will happen, this will predominate now. Okay, this will enforce predominant, is cation vacancy will be predominating, and again there will be increase in the increase in the sigma value. Okay, and that is very good for the T2. T2 means temperature where it is more than T1. So wherever temperature is less, it is intrinsic. Okay, wherever temperature is more, it is the extrinsic. Okay, so in T1 intrinsic region, what will happen here? But it is also a case of here we have shown, but it is less effective. This also is cadmium impurity here, but the effect is less here. Okay, so as you increase the temperature, effect will be more. So it will increase. Conductivity is more. So if you decrease the temperature, little bit less. Okay, effect is same of cadmium. Here also you can see here. Okay, so as you decrease the temperatures here, conductivity also decreases sigma value. Okay, this is inverse of temperature. So as you lower the temperature, so it comes in this way. As you go on increasing the temperature, what happens? Slowly it comes up to constant. Then again same thing here, like this. Okay, and again if you increase the temperature, again it becomes a highest conductivity, like this. Okay, this is a deviation, like this. Okay, this is how. So like this we can say this is ideal deviation. Okay, so from ideal it becomes the deviated here. Why? Because of the effect of the CD plus 2. Okay, so this is how in this we can show that the two regions here can be explained here, that is extrinsic region 1 where is sudden dip, and extrinsic region 2 here where there is sudden increase. Okay, this sudden increase in sigma value, this is sudden decrease in the sigma value. Okay, these two can be observed for NaCl when you go for this explanation. Okay, this you can explain. Okay, if they ask for the value. Okay, now here the effect of cadmium here in the AgCl, if you see the effect of the CD plus 2, okay, effect in on the conductivity of AgCl crystal here. So that what here we have seen here, effect of CD plus 2 in AgCl, and here we can see the impurity isothermal. Okay, this is isothermal conductivity. So here the effect of CD plus 2 impurity on isothermal. So T1 T2 we have done here, conductivity of AgCl. So here that is a extrapolation. Okay, so dash a dotted line we have shown here, like this, like this. So dash line here. So they show the effect of adding divalent anionic impurity. Okay, so effect is adding of divalent anionic impurity. So this is okay. Now here what we can see in the intrinsic region conductivity is independent. So I will write here in intrinsic region conductivity is independent. Okay, conductivity is independent of CD plus 2 ion. So in intrinsic, as I said here, so there is no role of the CD plus 2 ion. It is independent. You add or don't add. So intrinsic region, the effect of the CD plus 2 is independent of the CD plus. The effect of conductivity in AgCl is independent of CD plus 2. Okay, but in extrinsic region, okay, so you can see the interstitial conduction is predominant. So you have seen that in extrinsic region 1, okay, that is here in extrinsic region 1. So what will happen here? The region 1, the interstitial conduction predominates. I will write here interstitial conduction predominates. Okay, so interstitial conduction predominates, and sigma increases, and that is a sigma increases. Okay, interst predominates and sigma decreases. Sorry, interstitial conduction predominates and sigma decreases. In the region 1, and in region 2. Okay, so why it decreases? Don't get confused. Okay, why it decreases? Conductivity in the intrinsic. Okay, yeah, extrinsic one, interstitial predominates and sigma decreases. Okay, why it decreases? Because the concentration of Ag plus decreases, as I said already, because the concentration of interstitial Ag plus decreases. But if you see that CD plus 2 will increase the interstitial cationic vacancies. Okay, interstitial conduction, okay, predominates Ag, and that's why now if you increase with increasing CD plus 2, what happens again? If you increase the concentration of CD plus 2, that is in extrinsic 2 region, here, if you increase the CD plus 2 concentration, that as so in the extrinsic 2, so vacancy conduction predominates here. So what will happen now? The vacancy, whatever here it was less, the vacancy conduction predominates. Okay, with predominates, and the sigma rises, and the sigma value rises again, Okay, so this is what, because the vacancy of Ag plus increases, the increase in the CD as you increase in the CD plus 2 concentration. Okay, so this is what we have to we have learnt the effect of Ag plus 2 ions in the effect of the conduction of AgCl in the presence of impurities. Okay, as we have learnt in the what is the NaCl. Okay, so I think hope this electrolyte, that is alkali halide as well as AgCl conduction, they will definitely ask in the examination either one of this. So both mechanism and everything we have learnt in these two videos. I think this is more than sufficient. Here also very nicely we have learnt regarding the finding of the windows, where the movement of Na plus takes place from one window to another window, passing from three Cls, okay, Cl1, Cl2 and Cl3, 1, 2 and 3, making a 3 like this. We have shown it here like this, okay. So compactly, so they are arranged very compactly here like this, okay, like this. We assume that it is compactly, but we are not, it is not exactly compactly like this. By making a triangle here and cos theta and everything, we have learned this, where we got that window, that is r dash of 0.45 angstrom, and r double dash we got it as a 0.59 angstrom, okay. Squeezing and everything mechanism you have learnt in NaCl with diagrammatic. So this, and here AgCl, the two mechanism we have seen, interstitial and interstitial C. So like this, and we, lastly with the effect of impurities. So both we have taken the graphical presentation. In AgCl also we have taken graphical presentation and explained. NaCl also we have taken graphical like this. So where the effect of the this will be there, impurities like this, okay. So versus here like this graph we have taken, and here this is intrinsic, this is extrinsic, okay. How it does, this what we have explained here. So this is more than sufficient if any question comes in the examination to explain these two concepts, okay. Next we'll go for the solid electrolytes. Solid electrolyte, that is beta alumina, what heading is there for the video. Solid electrolyte, LYTES, okay. So what is this solid electrolyte? This is also called as fast ion conductors. They are also called as fast ion conductors, fast ion conductors, or also super ionic conductor, super ionic. This is just called as fast and super ionic, but that doesn't mean that they are very super fast, okay. Since they are solid, small conduction also it makes it fast. Is it right? First, because solid never conducts, okay, and that's why in that if it is conducting means we are considered as a fast ion or super ionic, okay. That doesn't mean the word, the name is there super ionic means it is very fast or super in nature. No, it's not super in nature, but whatever it is there, negligible. In negligible something it is conduction, that is why we are calling it as a fast ion conduction or super ionic conduction, okay. So most of the crystalline material, like for example NaCl, MgO, magnesium oxide, they have low ionic conduction. We know that they have low ionic conduction, okay. Although these atoms and ions they vibrate here, but they cannot accept, though here also vibration is there, but these ions are not escaping, though they cannot escape from the lattice structure, and that's why they are the weak conductors, or they are not the conductors, we can say, okay. But in solid electrolyte you can see, but here in solid electrolyte, okay, rather apart from in converse with this NaCl and MgO. So in the solid electrolyte, what happens here, the atoms and ions they some of the one component of the structure, I can say in solid electrolyte, one component of structure, okay, one component of structure, either it may be cation or anion, either it may be cation or anionic. They are free to move throughout the structure. They are free to move throughout the structure, see, this is important, okay. But in NaCl, MgO, definitely vibration of atom is there, but they cannot escape from the lattice, and that's why they are bad conductor. But here one of this free to move, one of the component, either cation or anion, they free to move through channels, okay, throughout the structure, and that's what it makes it the solid electrolytes, okay. So I can say they are intermediate. For example, if I take here normal crystalline solid, if I take this, and if I put some increasing defect concentration, if I increase the temperature here, I will take it as a temperature increase. If I increase the temperature, what will happen? This normal crystalline solid will have increasing defect concentration, increase in defect concentration will be there, or there will be phase transition here, phase transition. Definitely any solid is heated, as I increase temperature, there will be phase transition. That means this is about to convert to liquid or defect is being increased here. Now what is going to form here? After that it is going to form liquid. As you increase again temperature, it is going to form the liquid. So before forming the liquid, they are going to form solid electrolyte, like this, see here, like this, okay. So then they are going to form the liquid like this, okay. So this is how a simple I can show you. Temperature is here. As you increase the temperature, normal crystalline solids will convert to liquid definitely, but before converting liquid, it is going to change into two phases. Either there is a phase transition transition state will be there, or increase in the defect concentration will be there. This both will lead to solid electrolytes here. Okay, this both condition will lead to solid electrolyte, and finally they are going to convert to liquid. So this is what we can show. So in this case, so there is free movement of the one of the cation or anion. They're free to move through the channel, and that will increase. Okay, so that's why they are the intermediate between the normal crystalline, I can say normal crystalline solid with 3D structure. So this is having 3D structure, strong. So they are in solid electrolytes are the intermediate between the normal crystalline 3D structure and immobile atoms. There is no mobility here. Immobile atoms will be there, and between the liquid electrolyte here, and between the electrolyte which does not have any structure. Okay, so they don't have any don't have any structure, and but they are having mobile ions. So this is an intermediate. So mobile ions, immobile ions, structural component, non-structural component. So this solid electrolytes lies in between these two conditions or these two properties. Okay, this is what we can explain the we can define the solid electrolytes. Okay, so this is what we have to see, and they do not have any super I can say structures. Okay, with these solid electrolytes. Okay, so so they are very stable at high temperature. This is very important. These solid electrolytes, they are stable at high temperatures. Okay, so on cooling they transform to the polymorphs. Okay, if you cool this, they transform into polymorph. Polymorph is different state like this. Okay, they are called polymorphs. POLYMORPHs. Okay, on cooling they transform to polymorphs with low ionic conductivity. With low ionic conductivity. With low ionic conductivity. Okay, with low ionic conductivity. Okay, so for example, if you take some example of lithium sulfate or AgI. Okay, so they are poor conductors at 25 degree centigrade. If you see this lithium sulfate and silver iodide, they are very poor conductors at 25 degree, poor conductors. Okay, at 25 degree centigrade here. Okay, but if you increase this temperature to 572 for lithium and 146 degree for AgI. Okay, the structural changes. Okay, they are going to change now. The structural changes gives two polymorphs. They are going to give now polymorph. Okay, if you at this temperature, and they are going to change to now two polymorphs, that is alpha Li2SO4 and alpha AgI. See here. So they are going to change now from lithium sulfate to alpha lithium sulfate and silver iodide to alpha silver iodide at 145, 572 and 146 temperature. Okay, they are changing their structural activity here. So they have mobile now this condition they have at this condition now they have mobile Li plus 2. At this condition alpha lithium, so they have mobile Li plus here. Okay, and also Ag plus ions. In AgI they are having Ag plus ion, and the sigma that is your conduction to the value to nearly 1 per ohms per centimeter. Value of 1 ohms 1 per centimeter. Okay, this is what. And on heating the conductivity increases. If you heat this condition, again the conduction increases at the phase transition. This thing you have to keep in the mind, even for the zirconium. Okay, zirconium oxide ZrO2, this concentration of ion vacancy here, O minus to ion vacancy, the concentration of anion vacancy above 600 degree, above 600 degree centigrade. So it is more, and that changes gradually with increase in temperature. So if you increase the temperature, this change anion vacancy will be more. Okay, so ionic conductivity, if you see, it will be in the range of 0.1 to 10 per ohms per centimeter. See, very great. 0.1 to 10 per ohms maximum obtained here. Okay, in this case changes, and usually for most of the solid electrolytes, ionic conductivity is obtained from this range. Okay, very high. Okay, this is what you have to see. So the conduction here, and there is a large proportion of ion movement here at one time. Okay, and that's why they are called as superconductors, because large ionic motion will be there at one time. All Li plus will be moving, or all Ag plus will be moving at one time. Flow will be there, and that's why they are called as superconductors or fast ion conductors. Okay, so and they have low activation energy. They also have low activation energy. This is very much important. These all solid electrolytes, they have low activation energy for ion migration. migration. Okay, but in NaCl and all, we have seen that activation energy is more for ion migration, but here for solid electrolyte activation energy is always low. Okay, for NaCl we have some for NaCl what we have done, if you consider both cationic and anionic, cation and anionic, what we have considered here, so occurs near on the melting, the entropy of fusion is 24 joules. Entropy of fusion is 24. Okay, 24 joules per mole per Kelvin. This is for NaCl. Entropy of fusion is this much. Okay, and for AgI, if you consider now, for AgI, the beta to alpha transformation, okay, at 146 degrees centigrade, as we all learn now, at 146 degrees centigrade, which is called as quasi melting point of AgI, quasi melting we call it here, of Ag ions. Okay, the entropy of transition, it has entropy of transition around 13.5 joules per mole per Kelvin. Okay, this is what the entropy of transition is, 13.5 here for this AgI. And at melting point of AgI, okay, AgI, only iodide atoms, if you see, only iodide atoms, only iodide atoms here will be to become, only iodide atoms here will be disordered, as you melt, as you heat this at the melting point, this will be disordered. Okay, only iodide ions. Okay, so this and you see the entropy of fusion will be around 11.3. The entropy of fusion will be 11.3 joules per mole per Kelvin. See here. Okay, so entropy of fusion is 11.3 and entropy of transition is 13.5 for AgI. But if you see, the entropy of fusion for NaCl itself is 24, so high. Okay, but this two, if you combine these two, it will be equal to this. See, so that is what NaCl conduction is very difficult. Okay, so if you combine these two, the combined entropy of transition as well as fusion in AgI, so if you combine this entropy of transition and fusion in AgI, so what will happen? So that will be close to the entropy of fusion of NaCl, nearly only one, that is a 24 kilojoules per joules per mole. So this is what we can say, that the what is the NaCl solid that is a difference between the perfect ionic crystal like NaCl and the solid electrolytes like AgI during its transformation. See here, so that's why they are found to be very good conduction. They are found to be very good conductors, or super ionic conductors, or fast ionic conductors, we are calling this. And NaCl finds to be very bad conductor. Okay, unless it has been having the study of the effect of impurities or temperature, so many things as we learned in the previous video, unless that it will be considered as a bad conductor. But solid electrolytes are considered at the room temperature itself because of the small defects here, so definitely they are considered as a good conductor here. But as you increase the temperature, again the conduction will be fast. Okay, because you can see here the entropy of fusion transition is very less here in solid electrolytes when transformation beta to alpha, but in NaCl it is very high. Okay, so this is what I think more than sufficient for this video. Okay, make notes and understand these concepts very nicely. So in the next video we will go for beta alumina, okay, and AgI, that is silver iodide, solid electrolytes, okay, mechanism of conduction and everything. So this we will go in the next video. Thank you.